Happy to welcome my friend Pedro Ladeira. Pedro has over 12 years experience in the mining sector and specializes in pit and stope optimization, scheduling, mine strategy selection and designs, as well as electrification of mining operations. Has worked on projects across various commodities and regions, including iron ore, phosphate, manganese, gold, niobium, lithium, uranium, graphite, nickel, and copper. Pedro has also demonstrated leadership and business acumen as a former operations manager and team lead here with Datamine, where he was responsible for sales, maintenance, training, technical support, as well as customer service. Welcome, Pedro.
So yeah, today I'm going to talk about a simple topic that could be a one slide, but I managed to create 20 slides. It's a really simple approach and really interesting, but I would like to just share with everybody and see what was the output and show for everybody what was the outputs of that. I would like to create a good interaction with the audience. So I'm going to ask some questions during the presentations, and please raise your hand to reply or to say yes or no for that. And let's see if we can create this interaction. At the beginning, will be like really simple questions, but I will adding some complexity as we go. So let's start. Like today, I talk about the optimizing overburden contacts using pit optimization techniques. And to start with that, I would like to ask, please raise your hand if who has ever optimized a pit here. 99% of the room. Please, who has ever optimized a pit for a strategic deposit? A stratigraphic deposit, like a mineral sands or coal or a bauxite deposit. So I have like less than 10% of the people that raise their hand first. So normally, like in a general optimization, what's the first test that we do? Like we receive the block model from the geology, from the resource geologist, and we do some assessments in the block model. So who can tell me what's the first interaction and what the first process that we do with the block model when we receive it? Anyone? Mark.
Just a Thomas Gray curve.
Great. What else?
Validator.
What else? What's the manipulation that you do with the model before you run a pit optimization? Create the mining model. Perfect. And what we do to create a mining model? Don't be shy, guys. Excellent. Who said that? Yeah, we do a SMU analysis because we need to figure out the dilution and the ore loss. So we will figure out the size of our blocks to then run the optimization, because according with the size of our equipment, we will have the dilution for that, and we need to know what is the selective mining unit to run the process. So going through that, this is just an introduction of the selective mining unit, because it has an impact on the context and the background of this presentation. So normally in a truck and shovel operation, we assess the size of the equipment, we do a SMU analysis, and we will assess what will be the recovery and the ore loss impact, running the tons and grade curves. However, when we have a stratigraphic deposit, it's a little bit different, because your mining method might be not selective in a way that you can get some waste in the middle of the ore. If you're starting to mine that layer, that steam, you need to mine the whole layer. So you don't have your equipment doesn't allow you to segregate an interbody in the middle of ore seam, ore layer. So then the pit optimization can be performed for any type of open pit of ore body. And before the pit optimization, we normally do the SMU analysis. Who has ever done a SMU analysis here? And what normally you do in a SMU analysis? How you normally do that? Perfect. Reblock the model, and you assess in a curve what will be the impact. So more or less we get that. So you can see from the left to right, you just change the size of your block in your block model, and you will see that as bigger as your equipment, bigger will be your block, and lower will be your selectivity, and lower will be your cost. Okay, this is for a normal truck and shovel operation, where on the left side of your right side of your image, you can see like a digger just segregating the waste to the ore. But if you have a stratigraphic mine, like a mineral sands, you don't have the option to segregate that. So if you have a dozer push, for example, on this is a mineral sand example, so you have your layers from top down, you have the topsoil, your overbody, and your ore. If you have some low-grade material below the cutoff grade in the middle of the ore, sometimes you cannot remove that. You need to consider ore as dilution, or you need to plan better where will be your overbody contact to optimize it. So this is the key point, how we can choose this overbody contact, because we need to do that prior the pit optimization. So this is just some image showing a mineral sands example. And you can see that those are pushing the material for dozer mining units, DMUs. And as you're progressing to the side of your ore body, you just pushing the material and processing it. So let's think about the problem from a representation view. I've created here like a simple representation where you can see from the top down the layers. We have the topsoil on the top, the green one. We have in the middle some mineralized zone and non-mineralized zones. I'm considering non-mineralized zones that have material below the cutoff grade. And at the base, you have the basement and the bottom, and your ore body direction will be like kilometers for one direction. So if you think about this one, let's imagine that we'll do a pit optimization side of this representation. Consider that we need to define the overbody contact. I would like to ask, where would you create the overbody contact on this image? Like someone can indicate what would be like an ideal overbody contact from that you can segregate the waste to the ore? Anyone? Anyone would like to guess where would be the best position for it? In my mind, would be something here, right? Then you get all the waste material and you mine the ore material inside of your body. But if we do that, what we will do with these two regions that you have below the cutoff grade? Are you going to consider that as dilution or not? So we can create like this overbody contact and consider these two regions as dilution. But is this the optimal size, optimal way to consider that? So should we rethink about the overbody contact, and instead of have that this as dilution, have this overbody contact and have that portion as an ore loss? Or maybe this one and have two ore loss and a piece of dilution? What's the optimal contact that could generate to then run your pit optimization? So this is the key challenge that I faced in a project, and I was thinking like, how could I solve that? Not just choosing or just digitizing a string, but properly optimizing that to get all the financial parameters in perspective to get this contact. So this is the main objective. So was to develop a methodology that I could optimize the overbody contact and consider the financial parameters such as mining costs, processing costs, and revenue in a way that I can do that prior the pit optimization. So I'm going to present different methodology that I've used to generate this overbody contact. And I will present the pros and cons of each one. Although it's a real project, I will not, my focus here will be the methodology and the technique that I've used for that and not the numbers. And I would like to show the pros and cons and what was the result and what was my conclusion from it. Let's talk about the first methodology. The first one that I've tried was create a Datamine macro that will code the blocks, columns of blocks from top down, and summing the profit and the costing of these blocks and assessing if each portion of this interbody should be considered as dilution, or the material that's above the interbody should be considered as ore loss. So then, like with that, we could just replicate these calculations for all the columns of the block model and assessing these. So basically, the calculation will get, if you get the first portion with P1 and C1, is where we have the ore above the cutoff grade. So we have the profit to mine that portion as ore and the cost to mining that portion as overbody. As well as the second section, we have the profit to mine as ore, that waste material. Of course, will be a negative profit. And we have the cost to mining that waste material as overbody. So if we just do assessment and check that, we will understand and we will see what's the biggest benefit to the project. If we consider the overbody contact on the top, or and diluting the material, or the overbody contact below and having an ore loss. So doing that for the whole deposit, column by column in a macro, we can create and we can flag where will be this overbody contact. So this was the first methodology that I done. And I finally getting this for the whole overbody, whole model was right, the calculation was right, and I could flag everything. However, I have a con that I couldn't create and control how will be the contact over the blocks, over the columns, because I'm assessing each column of block. So if you see the column beside, maybe if you have a marginal ore, this overbody contact can just change drastically. So as you can see on the last one here, you have the overbody contact on below the waste material and then just above the whole ore portion. So like this angle between one column to the other column was really acute. So I cannot create an operational surface with that. So then I found this issue and I tried to think about the second methodology. How about we use the MSO for it? So the MSO, it's a well-known stope optimization tool for the underground optimizations. And I thought, let's see if I can create an envelope for the ore, and then I can control, as you can control in underground, how will be your stope. I might control that in the envelope. So I've run an MSO for a horizontal framework where you define your X and Y units and you do the annealing on the Z direction. So you could define, let's see, what's the maximal gradient that my dozer can push the material, and we can use this as a parameter for an MSO to control how will be the top as well as how will be the bottom of your mine. So let's see, I cannot have a gradient greater than 3 or 4% in the bottom of my mine. So like, how about using this MSO technique and running that for the whole deposit instead of having like acute changes in the overbody as the macro did. So this was the second option that I've tried, and I managed getting the shapes, was good, but the cons of this technique was that we need to use a defined framework for X and Y. So what this means, like we are increasing our scale from a column of block to a defined X and Y meters. However, we are not covering, we are still with the effect from one stope to the other stope on the top. We can smoothly that in the MSO. However, it increases a lot the processing time. So when you are thinking, if you are thinking about a mineral sands deposit with kilometers of extension, running this MSO and smoothing the contact stope by stope takes ages. And it's not the problem of the software, it's just like the problem that we are trying to solve here. It's a little bit different than the main purpose of the MSO. So then I thought, okay, we can do that. It has a long processing time, and there is some post-processing required. So then it's good, but could be done better. And then I thought, like, let's think about the real problem that we have here and the real challenge that we have here. I would like to create a contact surface that I would like to constrain to the maximal angles for the dosers and to delineate my contact between ore and waste. So why not use the pit optimization technique for that? So, but how could I use the pit optimization technique for this type of thing? Because normally the pit optimization will give me the bottom of the ore. I don't want the bottom. I want like the top of the ore and waste. So then I ask you, who have any idea how we could use a pit optimization technique on this case? You know? Sorry?
Invert the value of your own waste so that it treats the waste above as a positive value, and we're trying to find the maximized value of that, or that will also give you the contact region that you should be applying for the waste between the waste and
Yeah, it could be that, but how you will invert the value, but like in your ore, you have different grades for your ore. How you're going to consider the grade of your ore negative? To be really honest, I haven't tried your option, but like I don't know how I would consider the grade from ore as a penalty on this case, but might be one case. Yeah, my work. I haven't thought on that. Good. Anyone? Who? Flip the model. Exactly that, my gosh. So then, why we don't do upside down pit optimization? So what we do? If you multiply your z coordinate by -1, you have a block model upside down. Having this block model upside down, we could optimize it, and the software will take into consideration the maximal gradient as well as the grade of the ore when we create your contact, your overbody contact. So a little animation, and then this will be our overbody contact upside down. So yeah, I think that this could check all the boxes that are required for this proposal. However, we have some considerations on that. When I'm using this upside down optimization, we first need to disconsider the basement cost, because we don't want to impact the optimization by the basement. So we need to disconsider the base, consider that as an air box. The second point, we might have an edge effect. It for this case wasn't really relevant because it's on a mineral sand we have a huge deposit with kilometers side by side. So this edge effect was not relevant, but we need to be aware that if you have a lower, a narrow deposit, the angle from the optimization might impact your edge. And the last one is the operation to multiply the z coordinate by -1 is not really simple, because you need to adjust the whole prototype of your model and make sure that your IJK blocks are reordered in the right manner. So these are the three considerations of that, but this methodology shows that it's really efficient, and we could quickly use that to do many evaluations in terms of let's see with different cutoff grade what will be my overbody contact and how will be that, as well as we can assess the gradient of the overbody contact. If you like to reduce a little bit the gradient to increase the productivity of your dosers, you can just change this slope parameters inside of the optimization and rerun the optimization and check what will be the impact from the tons and grade curve. So it's really easy to rerun that against the other options. So that was really, really good. The cons, we need to manipulate the block model, and we have the edge effect as mentioned. So I have here some results and discussion slide where I just compare the three options. Basically, the first one is the software skills. So sometimes with macros, if you pass the macro for another person, so this someone that's not familiar with the macro is running that, you need to understand all the steps, all the process, and can be a bit tricky. So the MSO and the upside down optimization, it's easier from this side because they have a interface. The ability to apply the maximal gradient in a macro, you don't have that. In the MSO, you can do that in a X and Y framework, a limited framework, but in the pit optimization can extend for the whole size of the deposit. In terms of processing times, the MSO takes longer and the optimization is quicker. The ability to generate scenarios, MSO, and the optimization has an interface. You can just tweak and change the parameters and rerun. It's fast. And the visual validation. When you run the macro, you need to check if there is any exception on this macro. Maybe in the calculation that I show the P1 plus the P2 and blah blah blah. That expression might find some exception in some columns. So we need to validate a little bit this result to see if it makes sense in a visual perspective. And from MSO also, when you have the stope side by side, you might have some kinks and some changes in the stopes. And from the pit optimization, we know the Lash-Grossman algorithm, pseudo-flow algorithm, so it's really well known and it's really simple to trust and check that visually. So what would be the next steps after the pit optimization, of the overbody optimization, sorry, would be to run a proper pit optimization once you consider that above the overbody content is waste and below it's ore. Then we could create a series of overbody contact options to run the strategic scheduling inside of the final pit. So then we could flag the block saying with this price parameter, this is my overbody contact. With this price parameter, this is my overbody content. Create a nested of overbody contacts and bring all this information to the strategic scheduling, where you can play with it during the scheduling for the life of mine. So the different strategies could be applied, and in this example I'm using the MineMax for it, just importing these different overbody contacts and trying to, for example, at the early years of the life of mine, try to reduce the payback and get some high grade. So you can just change this overbody contact as you mine the pit over the years. So like if you have everything coded in the block model, you could tweak that and use that inside of your strategic scheduling. So yeah, it's a simple one, quick one, but I thought that was interesting, the way to solve this problem.
Pedro, well done.
Thanks so much.
Yeah. Thanks.